Hi and welcome to part 4 of this video playlist about the best methods for alkylating alcohols. In this presentation, I'll show you how to use alcohols as electrophiles. This strategy to prepare ethers is not as convenient as the use of alkenes, because the water formed during the reaction will deactivate many types of catalyst. Still, water as byproduct is much easier to handle than corrosive hydrogen halides or sulfonic acids. Most dehydrations of alcohols are acid-catalyzed, as shown here. Protonation of hydroxyl groups converts them into excellent leaving groups, and protonated alcohols are powerful electrophiles, capable of alkylating even non-deprotonated alcohols. Because ethers are more basic than alcohols, the initial product will be a protonated ether, which is still a powerful alkylating reagent. Thus, these reactions are reversible, and care must be taken to avoid the formation of product mixtures. Typical side reactions include the formation of alkenes, of symmetric ethers, and of catalyst-derived byproducts, such as for instance alkyl halides. Non-deprotonated alcohols are weak nucleophiles only, and any other nucleophile present in the reaction mixture can easily cause the formation of byproducts. This example clearly shows that carbocation formation is not required for alcohols to act as electrophiles. If the starting octanol would have been converted into a carbocation, much larger amounts of olefins or branched ethers would have resulted, because primary carbocations are unstable and quickly and irreversibly rearrange to secondary carbocations. In this example, however, only about 10% of branched ethers and olefins resulted. Secondary alcohols yield carbocations and alkenes more readily, but under optimized conditions, symmetric ethers can be prepared by acid-catalyzed dehydration of secondary alcohols, as in this example. Here, the main problem was the low boiling point of cyclopentene. Perhaps better results would have been obtained by conducting the reaction under pressure. Bis-terz-alkyl ethers are difficult to prepare, but a few suitable strategies have been reported. In this example, the dehydration was catalyzed by a zirconium salt and hydrogen chloride, and the target product was obtained in 54% yield. The preparation of unsymmetric ethers from two different alcohols requires either a large excess of one of the two alcohols or, as in this example, two alcohols of considerably different reactivity. Here, the secondary benzylic alcohol will form carbocations much more readily than hexanol and may also be more reactive in its protonated form because the carbon-oxygen bond is weakened by electron donation into the antibonding CO sigma orbital by the phenyl group. In this case, catalytic amounts of iron triflate and ammonium chloride were sufficient to catalyze the dehydration, and the unsymmetric ether was obtained in 78% yield. Phenols tend to be alkylated at carbon by carbocations or protonated alcohols. Some catalysts can, however, modify the carbon versus oxygen selectivity, for instance by forming a complex with an intermediate carbocation and thereby lowering the activation energy for the abstraction of hydroxide from the alkylating alcohol. The intermediate carbocation catalyst complex will show a different regioselectivity when alkylating a phenol than, for instance, a non-stabilized free carbocation. In this example, the etherification was catalyzed by a Lewis acidic gold-carbene complex, and no arene alkylation was observed. With Brønsted acids, arene alkylation was the main outcome. In this example, a cationic ruthenium complex was used as catalyst for the etherification of phenol with hexanol. Despite the low reactivity of primary alcohols as electrophiles, a high yield of ether was obtained under almost neutral reaction conditions. Most phenols are sufficiently acidic to be alkylated by a Mitsunobu reaction. In this example, a chiral secondary alcohol was converted into an alkoxyphosphonium salt, which then etherified a substituted phenol with complete inversion of configuration. Unfortunately, Mitsunobu reactions require expensive reagents and generate a lot of waste, and occasionally alkylated hydrazine dicarboxylates as byproducts. The Mitsunobu reaction is therefore only applicable to the preparation of expensive ethers. Here's a short selection of some additional recent examples, which you can also find in the description of this video. In the next presentation, we'll have a look at the reductive alkylation of alcohols with aldehydes and ketones. Although the strategy is mostly used for the alkylation of amines, in recent years some practical methods for the preparation of ethers have been found. See you then.